of airless planetary objects. Another invited talk. Welcome, Mihaly.
No problem. Other than it's a hard to follow. Which one is the advance? And graduate. Thank you, and thank you for the organizers to inviting me to give this talk. It is really hard to talk about plasma physics after such beautiful set of slides of real creators, but bear with me. So, it is really hard. So, what is this talk about is somehow in general talk about what would you see, what would you experience if you would be on the surface of an object without an atmosphere, or in some cases even without a global magnetic field structure to protect you. The incoming stuff, of course, is electrons and ions from solar wind, UV radiation, and interplanetary dust particles that are hitting you all the time. The biggest difference to these kind of discussions and your everyday life is the atmosphere. If you were to live anywhere else without an atmosphere, it would be hard. You would see all these and you would care much more deeply. But if you want to go and live and work on these surfaces, you will have to be aware of all these processes that might make that difficult. On the left is a plot, what happens in general from the 60s. On the right is the one that you might have seen yesterday when Jasper Hallekels or Andrew Poppy gave his talk. There are several things you notice. Certainly the graphics improved a lot in 40 years. The basic structures of forming the solar wind being supersonic with respect to the ions, subsonic with respect to the electrons, people knew those things. But there is an incredible amount of new detail and stuff that we learned since then. And I would like to, imagine that you are on the surface. I wish that logo would read differently, but that's the plot I have at the moment. These are the plans to land a capable set of instruments on the lunar surface. And this is really the other end of the discussion when Jasper showed you what the measurements of plasmas and fields show you in orbit. So what is that you see on the surface? You see incoming, some of the incoming electrons, some of them might be reflected. There are craters that are lit and dark. Probably there are strong electric fields, even in your own shadow, that you could set up. And it's a very exciting plasma environment to make measurements and learn how life would be there. And of course, some of it, we had a hint, and that's my only slide. You must have seen this before, that since the Apollo era, we have these hearsays of stuff going on, like a dust cloud being levitated at sunrise. This one actually is at sunset. The LEAM experiment, which shows data that the dust impacts rise and fall at sunrise and sunsets. And on its own, not a single of these observations make any sense. I cannot possibly tell you how it works. But as a whole, as a collection, all indicate that some sort of charging of dust on the surface, large electric fields would mobilize them and they transport them from one place to the other. And I would like to walk through what we think about it and how we can learn more about these things, even from simple laboratory experiments that you could do on the ground. Who cares? Why dusty plasmas and all these issues would have meaning to other communities than plasma physicists? And the argument that, lunar science and engineering should care about it because it can make the use and long-term stability of optical and mechanical devices, even the life of astronauts, make or break. You need to know about these issues. I have to tell you that actually basic plasma science is quite excited. How a plasma sheath would build and collapse on a diurnal period. What happens if you put a lot of dust in the plasma sheath? There's a lot of interesting basic plasma science to be learned on the lunar surface or any other airless object. And of course, planetary and astrophysical sciences should also care because once we identify this process, we can happily move it around the solar system and identify all other places where these processes are at work. And even astrophysics could care because if we could do these measurements right And on the surface, I would make an instrument that could distinguish between interplanetary and interstellar dust. We can probably even tell you the chemical and isotopic composition of interstellar material that comes towards these surfaces. So let's look at first the role of magnetic fields. And of course, we are all fascinated about the swirls. These are these albedo markings that early on people suggested that it has to do with magnetic fields and how the access of the magnetic fields to the surface would lead to differential space weathering. That is, a lot of stuff is coming in and interacts with the surface, versus where electrons and ions are somewhat excluded to reach the surface. And this is an experiment that you could do. Now, we oftentimes the argument can be made that, you know, these experiments really has nothing to do with the moon. There is no way that you would reproduce the vacuum. If you were to put the magnetic fields, the couple nanoteslas that exist on the surface, your device has to be as big as the moon. That's nonsense. So we're going to use much stronger magnets, different plasma conditions. But we are asking, nevertheless, the same questions. How does this process work? Who can get to the surface? Who cannot get to the surface? If there is differential access to the surface, can you do space weathering? Do you set up large electric fields? The questions can be asked in the lab and then change the parameters. If you have a model that can reproduce what we see in the lab, then you have some confidence that you could change those parameters, go and argue for cases on the moon, and argue for what are the right questions to ask. What is the right measurement to make? What is the right instrument to build once you have a chance to go there and make these measurements? So here it is. Imagine that we bury oh, I forgot to tell you, of course, how the experiment looks. Here it is. It's a heated filament that sprays electrons into an argon gas. The pressure is about 10 to minus 4, 10 to minus 5 atmospheric pressures. It will collide with the neutral argons, will make a plasma, and it will charge the surface. Underneath the surface is a refrigerator magnet door. And we just measure then the plasma properties and what happens, how the electric fields are distributed near the surface. And here is a scan of the potential. The magnet is underneath. These are the magnetic field lines. Ions are heavy. They don't get magnetized, or their motion is barely influenced by the magnetic field. They just come towards the surface, as they always do, even without a magnet. And then electrons, depending where you are coming in, if you are at the weak region, electrons have large gyro radii. They try to get to the surface, and as they turn around the field line, they will hit somewhere. Preferentially, actually, they hit on the right-hand side as they turn around, just by the geometry, as opposed to the guys that came in closer into the dipole. They have gyro radius that is very tight, and they are guided towards the strongest field when they intersect the surface. And you get a very uneven potential distribution. Here it is. The color code is here. The large negative potentials, positive potentials further away. And you see the structure as you move across very near to the surface. And every time you see a sharp change in potential, mentally take the negative gradient of it. That's the electric field. We are producing at places large electric fields. Thank you. You could actually bury the magnet in a different way. Make it such that the dipole moment is perpendicular to the surface. And then the story is very different. In addition to magnetic fields, in addition to electrons and ions, of course, you have ultraviolet radiation. And our colleagues who care about the sun, they will tell you that between solar min and solar max, the total energy output of the sun is changing a few percentile. That's very exciting for space weather and very exciting for the atmosphere of the Earth. But even more exciting for airless bodies is that the very short wavelength part, the UV radiation part, the part that can actually ionize, changing by a factor of several between solar min and solar max. So the amount of photoelectrons that you could generate from the surface of an airless object, in this case the moon, as a function of the photoenergy, or by the time you get all the way to the right-hand side, this is integrated, changes between 5 to 40 microamps per square meter. It's quite a bit. That's how you maintain the ionosphere, the sort of ionosphere of an airless object, by UV radiation that is quite variable between solar as the sun is changing. That can also be addressed in the laboratory, though these measurements are typically hard. Because the UV light sources are expensive, and you have to have quite a few of them. And furthermore, these experiments are handicapped by the fact when you shine light on a surface, it's really hard to control. Light will fall everywhere, on the walls of the chamber, on your grids, on your probes, everywhere. Photoelectrons are being produced everywhere. It's very hard to isolate the piece of surface that I am after. So we spent quite a bit of effort to make sure that we know what we are measuring, which is a message. If you want to make plasma measurements of the surface, it's not as easy as sticking out a probe. Because it also emits, the environment is changing. You have to be mindful what you are asking and what is the answer you will get and what you do with it. But here it is. We are shining light on this time it's zirconium. Zirconium has a very low work function, and it emits a lot of photoelectrons. We can beat the moon by far, which is all right, because we want reasonably small Debye length, so we can make the measurements that are somewhat localized. And then you could read out what happens on a surface that is actually, in this case, is cerium oxide, also a very good emitter. But cerium oxide has the advantage that you could buy a sheet of that, or you could have dust, the same material. And this wiggly line is that you are sticking in a wire, it's called a Longmu probe, and you make a bias voltage sweep from -30 to +30 volts. You are collecting a lot of ions, which is very few of them. These are just displaced. There is not a whole lot of ions. If you shine light on the surface, only electrons come off. On the right-hand side of this plot is the total amount of electrons collected, and the continuous lines in various experimental setup are all from solid surfaces, and the dashed lines are all from dirt, in general telling you that dusty surfaces are less capable of emitting photoelectrons, even of the same material. So far, we have done UV, we have done magnetic field, so I would like to turn away a little bit from the experiments and tell you that even the geometry of the surface, the topography, has a huge effect of what is going to happen on the surface. Imagine that we made a crater, and wish I had plots like the previous speaker, but this is our crater. It's a physicist crater. And we shine light on it, and we are making, and the solar wind is coming in, and this is actually the result, the cross-section of a full 3D simulation of the plasma with realistic electron and ion mass ratios. This is the UV illumination to the surface. This is a relatively small crater, only a couple meters across. And you could also look into the crater from above and notice that, well, yes, the day side is positively charged. You kind of can, there is something weird happening at the gradients when the surface is changing, but you could barely make it up that there is a crater. Wait a little, the sun will move in the sky. Now the sun is shining at 45 degrees. This part of the crater is still lit. That part of the crater is in shadow. And of course, the moment you see strong changes in color, rapid changes in the potential, those are strong electric fields. And now you can look into the crater and you see that, wow, that's kind of interesting. Inside the crater, there is a tendency to develop electric fields that kind of point inward towards the crater. Imagine that you put a spacecraft you land next to one of these. You could repeat the calculation. The symmetry is broken. Now you have to pay more attention about the dimensionality of this issue. Nevertheless, you could still run the same code. First, you should notice that even a spacecraft would make a tremendous difference in its environment. It will set up its own electric field structure. Wait a little, so the sun moves in the sky, and you would see that not only its immediate environment, but as it casts a shadow into the crater, it sets up electric fields within the crater. Mind your measurements. How long is your plasma probe that you have to get away from the spacecraft to measure something that was there without the spacecraft? Imagine that we have good models. So now I know the plasma environments, I know the electric fields, I can launch particles, and we can argue about the speeds, the size distribution. So be on the safe side, let's launch all particles with all speeds. See what happens as they dance around. So this is a flat surface, but we have done this calculation with a crater, and I will show that in a second. And what happens is, as you launch particles, many of them will fall back down to the surface, Many of them would actually have ejector speeds that are high enough to escape. If you launch something at 400 or 500 meters per second from the surface, on the moon it goes up to 1 kilometer high. If you overdo it for 2 kilometers or so, it will never come back. Some will actually be captured in the photoelectron sheath, and that's a talk on its own. This might be related to the lunar horizon glow, those mind-boggling images from surveyors that we are still struggling to understand. But imagine then, I will run a whole bunch of these trajectories near a crater. Here is the crater, was the same crater and the same plasma model without the spacecraft that we have discussed before. The black line across is the initial dust distribution, and it's nice and flat, uniform everywhere. Uniform at the bottom of the crater, uniform left and right from the crater. Launch and land dust particles for a couple hours. Let the sun set and rise for a couple days, and that distribution will change. Even after just one lunar day, you notice that there is a little pileup at the bottom of the crater. Do that for 15 days. There is a whole lot of dust piling up at the bottom of the crater. So you were lucky. That's an unusual distribution. It should be flat. You should do something different. Fair enough? Imagine that we pile all the dust on one side. Just as bad. But, you know, the computer can take it. So I pile all the dust on the left-hand side and repeat the experiment on the computer. Run it for a day, run it for 15 days. Soon enough, all the dust piles up at the bottom of the crater. Wow, now maybe our geologists would be interested. This is actually maybe relevant to the fact that as you can move around dust on surfaces, and maybe charging will do something on fine dust on these surfaces, the wiggly lines leads to the classification of asteroids, whether they are weathered or unweathered, maybe has to do with resurfacing processes. Were they anywhere near exposed to solar wind and UV enough to move the dust around? And of course, this kind of ponding, we have evidence, at least in one case, on Eros, when the Shoemaker-Near satellite landed on the surface. At the moon, we already noticed from LRO that the brightness of permanently shadowed regions, and it's not as silly as it sounds. UV from the interplanetary space shines into these craters. So if you look in UV, you can look into the permanently shadowed craters. And you would expect them to be bright, because that's where all the ice particles would accumulate. That's where the coldest there is. And they are dark. In fact, these are the North Pole and the South Pole, and most of these bright patches mark permanently shadowed craters. Wow. Maria, I wish she was here, noticed that this beautiful crater, then we have Shackleton. Now we have incredible data about the topography and everything. And she noticed that the bottom of this crater is dark compared to the walls. And there is a whole section in her science paper arguing about how curious this is. These are downward slopes and possibly. But you know, there is another way out, maybe. Just find dust at the bottom. Oh, I'm dancing away from the microphone, sorry. So, are there any other instruments or things that I would like to tell you about? And that is, of course, dust particles and measuring dust particles as part of your dusty plasma environment could give you additional clues of all the problems that we are discussing. Certainly, LODI would make a big difference. LODI, this is the flight model. It's done. It's awaiting shipment for the spacecraft. And I would like to draw your attention to its flight model that with minimal changes would be extremely suitable to put on the surface. And many of the movement of the dust and the impacts possibly could be measured with a modified LDAX. The modes are actually only in the electronics. So the TRL levels, if you want to argue, are still very high. So why would an instrument, and I would like to go back to orbit, how would an instrument help? Let me remind you what I expect LODI LDAX will find. First of all, whether this plasma lofting and feeding high dust clouds from plasma conditions would be there or not, I sure hope it's there. But those are tiny particles. They are very hard to measure. But they will show up in our, what we call an integrated signal, as you fly through the terminator region, 6 minutes out, about 20 minutes out from the terminator. These jungle or this forest of lines that these are single impacts. I will come to that in a second. The bottom line that our noise would be sitting on would be noticing the tiny, tiny dust particles that are not, we cannot detect them one at a time. Their collective signal will show up. Just as interesting is that in response to the incoming meteorites, some particles will be ejected to high enough speeds that we will intersect them. These could be large particles, at least bigger than 0.3 micron, that's large enough for us, and we will see them as single impacts. Now there is something curious about our celestial mechanics. As we fly, we could actually tell you that most particles will come from the surface, from a circle that is roughly, the radius of that circle is roughly comparable to the height of your spacecraft. That's how ballistic orbits work. So if you are at an altitude of 50 kilometers or so above the lunar surface, I can tell you that the dust we are measuring is coming from a spot on the surface that's about 50 kilometer radius right underneath. All right, so dust impacts can also be studied in the laboratory, and that is our beautiful big device that is only was possible to be built being part of the Lunar Science Institute. That's a 3 million volt electrostatic dust accelerator, and on the pipes come small particles, micron and submicron particles, up to speed of, at the moment, 60 kilometers per second. And we are working on making it almost 100. And actually what we are working is not the accelerator, it's our ability to make sure that we know they are coming. It turns out that the smaller the grain, the faster it goes, the less charge it carries, the harder it is for us to tell you that it's coming. So it's a technology demonstration, it's perfectly all right, and we are working on low noise electronics. And then of course we have this beautiful impact chamber that you could do all kinds of experiments. One of the experiments, for example, is to shoot dust particles into a target and see what comes out of it. And the way we do that, the simplest way to do that is of course, the impact on its own generates a whole bunch of electrons and ions of various compositions. The velocity distribution of those electrons and ions is modest. We could set up an electric field that would give all ions the same energy and start a horse race. If you have all the same energy, it will take you different amount of time to get to the other side. Half mv squared is identical for everybody. So the bigger the m, the slower the v. So your mass distribution, the composition can be turned into a time of flight spectrum. So on the other side, we just have a multi-channel plate and measure who is coming at what time. In the lab, you could make this a very long base, like half a meter, and you can have an incredible mass resolution. The dust particle comes in. Those red lights are actually not dust particles. Those are a laser aligning system, so we know where the dust particle comes into the chamber. It hits the target of any material, and then there is the grid that will accelerate the ions. They drift across, they get into the multi-channel plate, and we get a spectrum of the time of flight of the arrival. And you could have incredibly large mass resolution. Notice the nice separation between the silver isotope was 107, 109. And by the way, you could build instruments like this and fly them. And you could look for ice, not water atoms and molecules, ice. How do I know it's ice? This is the Cassini dust detector, the cosmic dust analyzer, in the earring. Those particles are made out of ice. We know. How do I know? This is the mass spectrum, and notice this forest of lines of a protohydrate, that's a proton and one water molecule, and two water molecules, and 3 and 4 and 5 and 6. You get this forest because the chunk of ice that hits the detector breaks up into clusters of ice upon impact. I can tell you that on the surface it was a chunk of ice. If it flies off the surface, hits the detector, yeah, I know it's ice. And if you look carefully, and I have later plots, you could even tell me minor compositions, for example, salts at Enceladus, and then our geology friends would run amok and will tell you, my golly, there is subsurface liquid ocean. You could fly an instrument like this around the moon. You could make it very compact. You could make the drift distance to assure high mass resolution somewhat bigger by folding them, making the reflecton type. And these are large spectra. You could certainly search for ice around the moon from orbit. So here I am at the very end of my talk. I took the liberty as to harvest out one of the pages of our friends, from the friends at League, and they were asking about what is the importance and how you get to the resolution of various questions, like the near-surface plasma environment, differential charging, and so forth. And I am all for that red dot because it says you should do it, you should land something on the surface. Absolutely. But I would also like ask them to consider possibly the weight of these other things that you could do in the lab. I think they will be very helpful to get ready to ask the right questions and do the right measurements. Thank you.
Thank you so much, Mihaly. That was great. Okay, lots of questions.
I was very impressed by your experiments, but as you know, lunar soil is a unique situation, and you've used cerium oxide. And the finer you go in lunar soil, the more nanophase iron there is. So when you're doing things on 1 micron scale, how do you feel about the fact that cerium oxide is not in any way, shape, or form a simulant for lunar dust?
I couldn't agree with you more. We have actually 1 spoonful of Apollo 17 lunar soil. We have made charging experiments, but you can imagine I cannot put that in and sprinkle on the surface, and so that's very precious. So we will come to you and ask you, is for example, GSC1 or MLS1, or is there some way that you could give us cheap material that we could do higher confidence measurements? We have used photoelectron experiments, MLS1 and GSC1. There's a small company in town, Zybeck, and Mike Weinstein is somehow, and I don't know the black magic, can do tiny iron particles, but maybe there are better samples.
Yeah, he's making an array of different sizes of iron. He's not making a lot of nanophase iron that are equally disposed. Nanophase iron is synonymous with single domain iron. Single domain iron is different than an array of iron that he's making. There is no simulant that duplicates lunar as far as that properties go.
So at the end, I think then the conclusion, we got to go there.
Okay, I see a question way in the back. Mark? Oh, I'm sorry, Carl. Sorry, hang on. Carlos, got the microphone.
This is really very interesting, Mihaly. I think you said part of my question. I wanted you to clarify particle size issues. But my real question was the timing. Your experiments, your computer experiments are very fascinating. And those were for a lunar crater and a lunar day, which are 14 days long. Does the timing make a difference, say, for asteroids, which could be a 7-hour day?
I'm sure it does. I always tell students, don't say anything on top of your head, but I do it anyhow. I imagine if you're a fast rotator, things will speed up. It's really the night lit dark transition that makes things work. It's really the transition which sets up these large electric fields, and on average they point towards the bottom of the crater. So if you do it quickly, I think it might happen quickly. As far as Shackleton, you have to bear with us a little longer because that's trickier. We have not done that simulation because that's at the South Pole, so we're going to be mindful how this will work out. But yes, I think the dust deposits go remarkably quickly. And I have done talks like this, and colleagues who work with the laser reflectors will point out time and time again. But we have not seen any degradation of the lunar laser ranging experiment. But that's not in a crater. That's not at the bottom of something that would make that space special. Maybe that is the answer.
Okay, we have 2 questions. They have the microphone, and then we're going to move on. So go ahead in the back first.
Yeah, I'm Mark Robinson, ASU. If there's a lot of, I don't really know how to quantify lot, but if there's a significant amount of dust being lofted to this 50-kilometer altitude that you're going to be flying at, since the surface of the moon changes only very slowly, so there's been billions of years of this going on, shouldn't the moon look completely homogeneous in albedo? We shouldn't see the mare because your homogenizing the top few microns with this dust being moved around over time?
I am capable of doing that at the bottom of the craters. As far as the large-scale structures go, you know, at some point there must be an equilibrium between impact ejector gardening that goes on very efficiently at all time, all places, and this very kind of delicate plasma effect of moving around just the smallest grains. These are tenths of a micron and 10 nanometer, tiny, tiny particles that I can shuffle into the bottom of a crater and keep it there. On a big surface, you know, and by the way, my efficiency of doing that is probably also a function of the size of the crater, so, and the location. So at some craters I can do well and pile up, make it a good centra. Some other craters I will be less successful. But with all honesty, at the end of the day, I don't know the answer. We'll have to work on it.
To find out. Okay, one question here.
John Keller, Goddard. Can you say something about the potential drops in electric fields that you're using in your simulation?
Yes. So a normal kitchen magnet is almost a kilogauss. Okay? So the gyre radius that we can do in a small-scale experiment has to be sub-centimeter. So, or the pi length is probably half a centimeter. The gyre radius of an electron is changing from that to even smaller. The electric fields we can generate easily. And by the way, hang on to your seat, it's a few volts per millimeter. This is a kilovolts per meter, quite hefty. So the next set of experiments is that we're going to sprinkle fine dust and see if we can actually move it on the surface. We have done some of those. We have done some of those experiments, and the dust in the chamber does move around.
Okay, great. Let's thank Mihaly for this wonderful talk.